So welcome everyone to the Winds and Currents webinar. And I'm really happy today to have Karak Saha, who's going to talk about improved blended sea surface winds, product for resolving hurricane winds. And Karak is a research scientist in the Cooperative Institute through the University of Maryland. So I'll let you take it away, Karak.
Thank you, Sarah. Good morning to all of you. Probably good evening for some of you. So I'll be talking today about this product of ours, which is called Blended Sea Surface Winds. And we had a version 1 previously, and we developed this into a new version called version 2.0. And this version has capability of resolving very high winds, especially associated with hurricanes and tropical cyclones. I'm Karak Saha, and I work with the Cooperative Institute at University of Maryland and with the NCEI, and the PI of this program is Weiming Zhang. Okay, so next slide, I'll be talking a little bit about the existing product, the version 1 that we already had and had been used by a lot of users worldwide. It was a quarter-degree spatial resolution blended sea wind, global blended sea wind data set with a temporal resolution of 6 hourly, and the data was from 1987 to 2018. And most of the data set that goes into developing this product are obtained from the remote sensing sciences products, and I'm showing here the different platforms that are used in developing this product. The major users of this product are from different areas, starting from the renewable energy industry to marine constructions. We have people who are using this data for marine forecasting and ship routing, and there are other users. There are also plans to use this data for the coral reef watch, and we have a lot of prospect users, which ranges from climate prediction to blue economy to U.S. offshore wind farming, and some of these users have been, they have contacted us, and that was one of the main reason why we wanted to have this, the new version that can resolve very high winds. So the blending technique that we used in our previous version was only a spatiotemporal blending that can average the weights are determined by normalizing the distances both in the space and time, and create some kind of a space-time domain and provide us an interpolated kind of data set which is gap-free. Although in our new product, what we have done is we tried to use, because we use the information, the direction information from reanalysis data set. So we have used both the GFS and ERA, and when we compared in our post-processing mode, we found that both the GFS and ECMWF have identical performance. But we used the GFS or the ERA just based on their latency time or the time of availability. GFS is more suitable for our product in a near real-time operational mode, and the ERA5 is more suitable for a retrospective product or research quality mode. So we are generating both in near real-time, and also we did full retrospective product development going back to 1987. We also provide a mask for this data set that actually gives you information like how the data set is filled and blended. Most of the light blue region that you're seeing are all satellite blended data set, which we call oceans, and there are some just to keep it like a gap-free data, we do use model input from the reanalysis data set. And this helps our users to determine or to be able to filter what they don't want to use. For example, if you're not interested in using any of the model data that we add in this product, you can just use this filter to just filter it out. This is a comparison with our data set with another product, which is a very well-known blended product developed. It's called CMEMS, and it's developed in Europe. And the comparison is shown here for both the U winds and the V winds, and it shows that the differences are very near to zero. It's around 0.03 meter per second. I'm also showing the distribution curves, which fairly shows that both the products are very near to each other. However, and this is another comparison between the CMEMS and our product, and it clearly shows the mean differences are again around 0.03 meter per second throughout the globe, and there are some extreme values, and we'll be talking about that. The RMSD also shows that around in the mid-high latitudes, the differences are a little bit high, which is around 3 to 5 meter per second. But other than that, around the tropics and the equatorial region, it's around 0 to 2 meter per second. Now, coming back to the problem that we wanted to address here. This is an ERA 5-10 meter neutral wind for a particular day. And what I've pointed here is one of the cyclones, Cyclone Fantella in 2016. And the winds that were reported by WMO, and the source for this data is IB Tracks, was approximately 59 meter per second, and the ERA data was nowhere near that value. So, and we try to see it in the Siemens data. It's also a blended product, and the values that we got in the Siemens were also similar to the ERA, and so it was very much, almost around 25 to 30 meter per second. We checked it in our data set. The previous version of our data set was also similar, but then we tried to add some of these new satellites like SMAP and AMSA2, and we thought that if we can we are able to blend these new satellites data set in our product, maybe we'll be able to reproduce some of these high winds. But just using the technique that we were using that I mentioned previously a couple of slides back, that used spatiotemporal blending, which uses an average weighting, or it gives an equal weightage to all these platforms. Just doing that, it doesn't help us, because what it does is when we keep adding more and more platforms which are not able to derive these high winds, it actually weighs down the average. So when you blend with different satellites, this kind of a traditional blending, it doesn't work, and you always underestimate. So what we did was we tried to generate a new process and try to develop an optimal weighting factor on the basis of the random error of each of these product, or each of this data set that we are blending in our product. So we use a simple triple collocation method to generate these errors, or to generate these random errors for all these products. And on the basis of those error information, we develop these different weighting functions or weighting factors for each of these products, and then we achieved an optimal fusion technique that can retain the high winds along with the low winds, and we just don't give full weightage to a very high wind value. We just give that weightage only when the error is low. So it's kind of inversely proportional to the error. So if the error is low, we give more weightage to that platform. So this is an outcome of that particular technique. So what happened is on your left top, this is our previous version. The same storm that we saw a couple of slides back, the values were around 28 meter per second. But when we added the SMAP data using the technique that the data fusion technique that we use, the winds that we got around the hurricane area was almost equivalent to what were reported by the WMO on this particular day. So it was around like 71.9 meter per second. So basically what we did was our previous version, from the previous version, we redeveloped it into a new version we added more satellites to it, and the major ones were the SMAP and the AMSR2 satellites, and then we were able to develop this a new data fusion technique to resolve these high winds, and we do it on top of the the spatiotemporal weighted interpolation that we do. And having said that, we also use the GFS and ERA 5 data, both, as I mentioned, for our near real time and for our the science quality data. And we end up having a gap-free output. So we have 6 hourly blended sea wind vectors and the wind stresses. We also provide the daily wind vectors and the respective stresses. We also provide the monthly and blended ocean wind climatology. Okay, so this is just to show what are the difficulties of using only these 2 satellites that we have that can really delineate these high winds. So because of so on the left hand side, I'm just showing that I just added its map data into our other wind data set that we have, and it was not able to really delineate or resolve the high winds that you are seeing. The values are not very high. It's because the SMAP SWAT, if you see below, these are 2 figures that I'm showing, it totally missed the hurricane in this figure, and because these hurricanes are very fast-moving entities, so it's very hard to catch them just using a single product or even kind of using a couple of other products. So when we added AMSR2, and we were lucky here that the AMSR2 had a pass and it could see the hurricane eye, and we were able to, when we added the AMSR2 data, we were able to get those high winds. Now the problem is, what if the SMAP and AMSR2 misses, and both of them misses, then we won't see that in our product. So if we have more and more such data set that can resolve high winds, and we have this technique to blend these products in our data set, and that provides us a good result as compared to when we don't have these data sets. So here, what we are seeing here is AMSR2 is acting as a complement to SMAP, and as we keep on adding more such satellites, it will definitely improve our product. This is an example of so I'll be showing a couple of examples here. This is Hurricane Irma, followed by Jose and Maria, and on the left hand side below, there's a comparison along the track with the IB track winds and the different data set that are available for. So we have the um, uh, in orange we have the our product in version 2, and the green is CMEMS, the red is ERA5, and the black is our product version 1. And we could see that the orange is very close to the blue line, and it clearly shows that we were most of the days we are able to capture those high winds. Yes, there are some missing days, and that's basically the reason. I mean, the reason for that is basically what I showed in my previous curve. If the swath is missing the moving hurricane, we won't be able to see that. But it can be resolved if we have more such satellite data. This is another example. It's a super cyclone Amphan that came in Bay of Bengal, and here also you can see the base track of the storm. The mean sea wind is shown here, and the blue line is the IB tracks data. Along with that, the orange points are the and our version 2 data set, and the version 2 data set, it does provide high winds very close to what the IB tracks data set provides, and the maximum wind ranges from 0 to 75 meter per second in this particular case. So as we have and I would repeat myself here, like more as we have more and more such data set that can resolve this high wind, we have this technique to blend it in our data set and keep that wind or the high wind there in our data set as well, so which is not visible in any of the other blended or reanalysis data. I'll be talking a little bit about the offshore wind, the program that we are also working on using our data. And this is kind of like a working project going on with one of our Lepanta intern. And what we are doing here is basically generating a high resolution data set for the coastal US and trying to generate different metrics to identify some of the proposed or to identify some of the region where good wind farming can be done in and around the US coast. These include some of the already operational and some of the proposed stations for wind farming in the US coastal region. So these are some of the different metrics that I've been talking about. On the top left is an effective wind speed occurrence, also derived from our product for the year 2020. And what we see is like, it gives a sense of, how much percentage is the wind between 5 to 25 meter per second. And mind you, this is at the hub height we are talking about. Also, we are generating the wind power density curves that can provide also give information about where most of the wind power, or where the more efficient places to do this wind farming. On the top right, we are also providing a trend plots over the US region, and this trend is developed using 35 years of our data set. We're also simulating for different stations this wind turbine power output in megawatts, and this is just very station dependent and also dependent on what kind of turbines and what are the different specifications of turbines that can be used or are used operationally in these wind farms. So this is just to give a flavor of what we are doing right now. So just to summarize, it's kind of next generation of our blended product. and we used a simple random error based weighting method to blend some of these some of these platforms which really are good for high winds like SMAP and AMSA2, and we'd love to have more such data set in our product. We are also looking forward, like, we are trying to improve this blending technique, and we probably we are actually working on developing this a multi-sensor blending technique further, and one of our interest is using, especially for the US coastal area, using the SAR data and Cygnus, and also the proposed Wacom. I'm not very much familiar with it, but what I've read so far, it's I think it'll be a very good data set for our product as well. And apart from that, we are definitely supporting some of the other programs that are NOAA specific, like the offshore wind and the Blue Economy Initiative. And thank you for listening to me. I would be open for any questions that you have on this data set. And this data set is, this is the link to our publication that we have for this data set. And this data set is in the pipeline for getting archived and will be available soon in the public domain. But if you are interested in using or testing this data set, please contact me. I can provide a sample, or I can provide this data set to you. Thank you.
Thank you very much. This was really great. We have time for questions. So if people have questions, you can raise your hand or call out. But maybe while people are thinking, I'll just ask a couple basic questions. The Wacom, now Odyssey, proposal is for vector winds. Does your method differentiate between wind speed measurements from passive systems and vector winds, and does it make a difference?
No, currently we are not doing that. But I think maybe in future we will definitely love to have something where we can have this kind of a differentiation.
And one of the challenges for the Odyssey proposal is that it uses a frequency that doesn't do too well in rain. So that can be a challenge in the middle of a big hurricane. How much, I don't actually know, how much is the peak wind right at the point of peak rain, and how much does that matter?
Yeah, I think if I'm not wrong, the Odyssey is in Ka band. Is that correct? I'm not sure. So it will definitely have rain attenuation.
It will have rain attenuation, yeah.
Yes. So for our product, I think it will be more like if we use like a lower frequency data set, which we are able to obtain through the SMAP and AMSA2. Although SMAP was not really meant for wind, it's just for soil moisture. So but we found that this data, especially for hurricane resolving wind, it's really good. But yes, other than that, the more the data we have, the less amount of gap filling we have to do. So so definitely any data set that provides us more or high quality wind is useful for us. We don't have to rely on any model or reanalysis data to fill those gaps. So yes.
And I think the flip side of the rain attenuation is that um, the type of high resolution scatterometer envisioned for Odyssey
True.
has 5-kilometer posting, so much higher resolution than we typically get out of passive microwave systems. And
True,
that
true,
makes it
very true.
possible to potentially dodge patches of rain and see high winds adjacent to rain or high water vapor
Absolutely.
areas.
Yes, and that is one of the and that reminds me, like, when we are talking about the regional product, that's the US region-based product that we are trying to develop here, we would definitely like to have a data set that are very high resolution, like 5 kilometers. And even like I'm trying to see if we can use the SAR data. The Cygnus is also there, but its resolution is not that good. But yes, SAR and probably these kind of high resolution scatterometer data set that we are talking about will be very much useful, especially for generating a product that is regional. I'm not sure about global yet, but yeah, I mean, we are starting like to start with. I think it will be a good addition to our regional product.
I was wondering also how your product compares with the one that is now at Remote Sensing Systems that's referred to as CCMP, but maybe it has a different name as well. So
yes, it's called CCMP. Yes,
yeah.
I don't have the comparison offhand, but what I have seen is when I compared my product with CMEMS and as compared to CCMP, there is a slight shift or there is a slight bias between our product and the CCMP. Although I have seen that same bias existing in when we compare the CCMP with in situ, and it's that bias is actually less in our product. Although it's an ongoing study, so I would definitely like to do more on that and maybe come out with some results. What so far what we have seen, I have compared like couple of in situ station data for the whole time period for 35 years. And so far, it looks that our data set has less bias than the other data sets.
In comparison to in situ obs.
In comparison to the in situ data set. Yes.
Yeah. And that's interesting because I think CCMP was trying to use the in situ data as one of their anchors to correct.
It does, and that's why I didn't want to comment on that. Like, I have no full knowledge of how true it is because it's just a couple of stations I have compared. So I probably have to do a more global analysis for that. Right.
Yeah. So one of the ongoing questions for blended products that use NWPs as a source is that the NWP products are assimilating the satellite winds. And there's often a question of how circular this is or how much information is being used twice, or if anything is withheld that is available as an independent test. I don't know if you've pondered this or have a perspective on what the right approach is.
So if I understand the question correctly, like, do we provide that information, like how we are using this data set?
Yeah, well, sometimes the question is, do we even know which wind products, the ECMWF or any other NWP product, what are they actually assimilating and what is independent?
Yeah, that's a good question. Yeah, I mean, I probably at this point I haven't thought about that, but I think it's a very interesting question, and I definitely like to look into it. Like, I have to probably go into and check the details on how they're assimilating it. Because so far what we have seen is most of the reanalysis or any other data set are definitely underestimating especially for the high
Mhm.
winds
Mhm.
cases. But yeah, I mean, definitely I'll look into it.
Yeah,
Wai-Ming, do you have anything to add?
Well, if I can add a comment, probably you mentioned that already earlier. For the wind speed, the NWP or reanalyzed data only take effect when there is data gap. It's no satellite data coverage, and that area is relatively small over the global ocean. But we do use the in the model speed direction. Direction to field
Direction.
direction. Because the reason is that for global quarter degree 6 hourly just does not have enough
Mhm.
satellite measurements for field direction information. So yeah, there do impact, but there are impact are limited, and yeah, I think there is still a topic to research how much difference between the yeah the gaps when we have gaps left by satellite data versus the without using the model results. Yeah.
Mhm.
Yeah. Thanks, Wai-Ming.
I think one of the things the NWP products do is to decimate or produce super obs from the satellite products. They just use a lot less of the information than is actually available.
Okay.
So I can keep asking questions, but if anybody else has questions, you should please go ahead and raise your hand, put them in the chat. So I was also wondering about I think one of the questions about really extreme winds is why are they missed in other products? Is it because they're too small a region? And so having high resolution winds is really important, or is it because the retrieval algorithms simply don't know how to identify really high winds? And so they get missed in some of the products or suppressed
I
in
think,
NWP.
yeah, yeah, that's a good question, and I think that it's a little bit of both, because what's happening here is there are some products and more like especially the products that are low frequency products, they are able to identify these high winds. Although in case of hurricanes and tropical cyclone, yes, these are moving very fast and sometimes you miss them. But sometimes you do get those high winds, but it's also the process that we use to assimilate them together or blend them together, which basically I think normalizes everything. So that's what we were also trying to tackle here in this product, that somehow we come out with a process which gives a different weightage to different platforms, just on the basis of the fact that how good the data set is. And we are not doing it like randomly. We are actually calculating the errors on the fly for the data set that we use, and then use that information to generate this weighting function.
That makes sense. So if there's an area of a storm that has winds at 75 meters per second, how big is the area? How long
How
does
big
that
it is?
last? Yeah, how much spatial area or how much time at a given point does that represent as a function of the total?
Yeah, right. It depends really on the storm size. Like it can go even up to like hundreds of kilometer to like 1/10 or two. It really depends on how big the storm is. But the bigger the storm is, it is easy to capture those high winds, I would say. But then the real issue here is when these blended products, they bring all these information all together. Somehow, when they blend it, that the real information dies down when you really blend it just using a normal spatiotemporal function or any other kind of interpolation you do. So that's the
that makes sense.
major thing.
So finally, I guess one of the questions for any new satellite is for engineering reasons, and everything is going to end up on a sun-synchronous orbit. For Odyssey, I think we're looking at a 6 a.m., 6 p.m. overflight time. In your, with a wide swath, so it'll cover a lot of area, but in your assessment, is there a particular, you've said that just filling gaps is really critical. Is there a particular time of day or particular gap filling strategy that would be optimal for what you're doing?
Yeah, right now what we have is like a 6-hourly product, and I think sun synchronous 6 a.m. 6 p.m. Will definitely add more data set in at least 2 of the times. So, and what we do is when we say 6 hourly, we take 3 hour before and 3 hour after, for the blending technique. So definitely it will be useful in using even a sun synchronous data set. Yeah, that's what I can think of.
Yeah, Sarah, that's the question. You can add one more comment on that. Yeah, I mean, I do wish, the satellite mission groups are coordinating with each other, and Clark showed that what's available satellites, have a different time, equator processing times. I think, when I first published the paper of sampling studies on this wind, the European does review that paper. They thought they will use that results coordinate their satellite mission timing. But I think I'm not sure. The military satellite missions, NASA satellite missions, and different satellite missions, if they can coordinate and just avoid repeating the same place, or repeating either for validation purpose, but for general sampling purpose, if we can separate that would be great.
Yeah, and I think that CEOS, the global coordination, has made a strong statement about the importance of having potentially 4 wind vector measuring satellites with well-coordinated orbits. But there's this constant engineering push to get something that gets lots of sun exposure on ascending and descending tracks. So there are challenges in terms of the design, choosing any or arbitrary orbit. Other questions? Well, if not, we'll wrap up. This is really great. I'm excited to think of looking at this data product, and I'm sure other people will also be interested in getting in touch to get early access to it.
Yeah, sure, and I'll be happy to help. I mean, and provide the data set if anyone is interested. Definitely. Thank you for inviting me.
Yeah. What's your timeline for an official release of the data?
Well, I would say it's in the process right now, and probably I'm hopeful that in a couple of months we'll be definitely trying to put it outside. We're right now working on it.
Sounds great. Okay, well, thank you very much. And thanks everybody for showing up.
Thank you.